All right, so we're coming up with the derivative function itself. So what does that mean we're going to do? All right, so then, so we're going to do the limit as h approaches 0 of f of x plus h minus f of x over h. All right, so then what's the procedure? All right, so then just because it's obnoxious looking doesn't mean that's not what we do. So then it looks like it's this. That's a B. All right, so then this becomes all of this. And then all of this. Does this look okay? Okay. So I think that's probably simplified as far as you're really going to get. So now what? So we gotta subtract the original f of x, right? So then I'm gonna, hopefully there's some like terms. Is there gonna be any like terms, I think? So I'm gonna say, I'll do this in like red. Yeah, so then it's gonna be, right, it's gonna be minus ax squared plus bx plus c. And again, this is in, be careful because that's in parentheses. Okay, so then that means that the ax squareds are gone, the bx's and the c's, right? Is that okay? So then what we're saying is we have the limit as h approaches 0. And so then the numerator looks like it's 2ah x plus ah squared plus bh. Factor out an h, and so then we would have, so it'd be 2ax plus ah plus b. Oops, so it's not over anything anymore. Is that okay? And then now we can direct substitute that, right? So now we can direct substitute, and basically that term with the h is just gone. So then we're saying the limit of all that would be 2ax plus b. Is that okay? And so then you could, part B, you could just re-go through it, but, that's in the same form. So you could just say for part B, right, you could say, oops, come on. Right, you could just say, okay, well, so A is 4, so this is part B. So you could say A is 4. So 2 times 4x, and then b looks like negative 3. So then 8x minus 3. You can go through it again, of course, but right, I mean, that's kind of... And so what's cool about this one is that's always going to be what the derivative of a parabola is. Now you don't have to memorize that, because again, we're going to talk about some way easier techniques. Okay, so, but that's what that is. C, okay, so then C, so then really we should write this with the notation like this. And so then for part C, they're saying 1. okay? And what is that 5? What is that? Slope of the tangent line where? At 1. For that specific, for B. Okay, is that okay? Anything else? Hopefully you're feeling okay about limits now that we're already through limits. Like, hopefully they're making a little sense. I do like going over these. So this is just the review things. I like doing them after you gotta know what's going on. So this is on just a page before there on 143. So it says use the definition number 1. So that was the x minus a one, not the h one. For the slope of the tangent line to explain how the slope of secant lines approach the slope of a tangent line. So
you use like x and a on either side of the point you're looking for of where the tangent line, where you're looking for tangent lines. So then you do so either you're looking for tangent line 2, you do f1 and f3, or closer than that.
Okay, so you're doing like an estimate. So just in general, how does it work? If like you said, if you were at 2, describe how so you could be going to 2 to 3, and that would be a secant line. Now, of course, that's an average. So then what happens to get it to an instantaneous?
You get closer and closer to.
Yeah, you just shrink up that, A and X get closer and closer together. Okay. Explain why the slope of a secant line can be interpreted as the average rate of change. And maybe think of when we drove to where did we drive to? The dog rescue place.
Mm-hmm.
So how is the slope of a secant line? How can that be interpreted as the average rate of change? Yeah, and so really it doesn't matter what happens in between. Okay, it's just where you start and where you end. Okay, so you go super fast on the way there, but then hit when they were doing those trees or whatever, and you had to stop. Okay, so then your average rate of change is still whatever it was, just the slope. Explain why the slope of a tangent line can be interpreted as the instantaneous rate of change. Yeah, because it's just the tangent line at 1 point. All right, so that's pretty good. Where are we at? For a given function f, what does f prime represent? The derivative. And what is the derivative again? The slope of the tangent line, right? So the slope of the tangent line is perfect, or you could say the instantaneous rate of change. Okay, those are interchangeable. Given a function f and a point A in its domain, what does f prime of A represent? The slope of the tangent line at that exact point. Okay. Explain the relationship among the slope of a tangent line, the instantaneous rate of change, and the value of the derivative at a point. What is it? It's the same thing. Yeah, all of it's the same. Number 7, why do we use that notation? What is the point? To remind you of something. Is the change of y over the change of x. So it's to remind you that you are just doing slope. So again, one of the challenges in, we're not doing calculus, engineering calculus. Okay, so we have to remember why we're allowed to do all this stuff. And so this is to remind you, as we get further and further away from it, that we're only everything is slope. We're just talking about the slope at this 1 point. Okay, so that's to help you remember. And so then 3 other notations. Okay, so then dy dx works. Give me another one. Okay, usually we don't do that one, but that one's okay. There's another one. This one's going to be the most used, or it's very similar d dx. Both of those are going to be used a lot. The other most used one is kind of one we already looked at today.
Did they do like F prime?
So f prime of x, that's gonna be probably the most used in the long run. One of these three is gonna be the most used. Sometimes we're gonna see y prime of x. Then there's that d that they'll throw in every once in a while, but that one's super rare. Okay, so if you know these ones up here, then you're fine. So far so good? It's gonna be a fun day. Of the year. No, you guys will like it. Alright, one more of these, or well, three more. For linear functions, alright, straight lines. The slope of any secant line always equals the slope of any tangent line. Let's get a linear function to look at. Yeah, there it is. Alright, so again, they're saying,
True, because it's like moving at a constant rate.
yeah, very good, right. So it's moving at a constant rate. So the slope of any secant line is always equal to the slope of any tangent line, right? Because like Dina just said, it's moving at a constant rate at all times.
And like variation.
There is no change in line or change in x.
No, there still is,
Well,
right?
Like you're moving a distance, but you're like moving at the same rate.
But you're always doing the same rate. So no matter how close we get, like if we do an instantaneous, it's still changing at that rate at all times, okay? And this is going to lead to kind of what we're going to talk about here in a couple minutes. The slope of a secant line passing through points P and Q is less than the slope of the tangent line at P. So we should look at another. So what if I do this one? Boom. All right, so then let's do P to Q. Right, then its secant line would be, yeah, let's try that again. How about that one? That's a little bit better. All right, and so then there's the tangent line. So yes, but then the question is it always true? You say no?
No.
So no, it could be, but it maybe not, right? Because like, what if it was like this? Or what if it was like this? Okay? So not always. Consider the graph of a parabola. For x being positive and h being positive, the secant line, okay, hold on. Let's look at a parabola first, huh? Right, so they're talking about this one right here. All right, so then x being positive, so we're over here somewhere. H being positive, so just a little bit further down. The secant line through these 2 points always has a greater slope than the tangent. So if we're here, that's where we're, why is that not working? Why am I, what's happening here? Well, it's not drawing very well. But so if that's the tangent line here, and then we go to here, right, so they're only saying to the right of the origin. So again, it's saying, is the secant line always greater than the tangent line? Then yeah, because it's moving further up as we go. Okay? Is that okay? All right. All right, now the fun part. Right, so hold on. All right, so firstly, what I want you to draw is the original function f, but I just want it constant. How do you draw a constant? So it's going to be linear. How are you going to draw a constant?
Is it this?
Well, they're linear. One is what's constant, it'd be like you graph 3. That's an example of a constant. So yeah, so what Trevor has, yeah, so that would be a constant. Okay, all right, so that is your f. Now what is a derivative again?
It
It's
is
a F
the
prime.
the tangent line.
The slope of the tangent line.
Okay, so we're talking about slope. Okay, so your job now is to draw, given that one, I want you to draw f prime. Right, so then the derivative is always the slope. So then in this case, what is the slope? Well, it's 0. Okay? All right? So is that okay?
Yes, that makes sense.
Right? The slope of your function was 0. Okay, so then,
New plane.
okay, so leave it somewhat accurate, so just erase the line that you got. And now, what I want you to draw is any linear function you want. It doesn't matter to me. I guess if you want me to choose, I would say make the slope not a fraction. And again, you are drawing f. And then I want you to draw f prime. What's that?
Do they not clean your board?
Apparently not. Yeah, I know.
That's nice though.
I asked the guys, like, if I leave you a note, can you do it? And he said, yeah.
Leave him a note.
So far, what we've done is, if it was a constant, the derivative was 0. If it was linear, the derivative was the slope. Okay? So now what I want you to draw, still have like a somewhat accurate one, but I want you to draw all linear stuff, but with jagged like corners. So you don't have to get crazy, but do like at least one or two, at least one corner, probably 2 corners. So like kind of think like of an absolute value.
How many jagged corners?
Let's do at least 2.
Oh, like that.
That's supposed to be on too, just like that?
That's fine.
I really out here just copying your sheet. For real. I'll go backwards.
Okay, so again, the jagged thing that you drew is your f. Now I want you to sketch f prime. I'm going to talk to my YouTube people, or Adrian, however you want to think of it. So ignore me for a second. So these slopes aren't accurate, I just estimated. So right, when it was a negative, so these are still linear, so the derivative will be constant, right? But if your slope of your original is negative, then you better draw the constant part below the x-axis. So you got, but you're saying it's 2 different things. So actually, you failed the vertical line test, though, don't you?
I don't know.
Well, so your derivative still is a function, so it still has to pass the vertical line test.
So I can only have one line?
Yeah, you can only draw one line at a time.
Dot at 0, wouldn't you? Because at that instant you point at 0. Right?
Okay, so careful. So Trevor just said something that is, we got to talk about here in a second once you guys get it up there, okay?
Okay, I'm confused.
All right, so now let's talk about these jagged corners. If you're coming from the left of one of your jagged corners, it's producing a certain slope. And then all of a sudden you get to the other point and it immediately is a completely different slope. There was no gradual change.
So is the slope at that point 0?
So no, what we're going to say there is that, kind of think of this as like the limit from left and right. So they kind of have to agree. So since we're at these jagged points and it just jumps real quick, then what we would say there is it is not differentiable there. And so the easy way to remember this is functions are only differential differentiable on curves. Okay, so any spike, there's also called a cusp. Those you can't do, okay? So anything that comes to a real jagged point, you can't take the derivative at that point. Maybe other places, but not there, okay? Likewise, there's going to be some functions that have vertical lines. We cannot do it there either. Okay, so that's a very important point. Okay. So are we kind of happy?
I'm happy.
All right, so then get rid of your scale. Give me you don't have to worry about scale anymore, but you do need all 4 quadrants.
I think it's just your whiteboard.
What's that?
Your whiteboard, it's just a track.
And so then draw yourself a parabola. And I don't care if it's upside down or right side up, it makes no difference to me. Give yourself a parabola anywhere you want it. And that is your F. I want you to sketch F prime. Right, think it through as in, right, the derivative that you're trying to draw is just the tangent slope at every point. These won't be a bunch of lines. Right, so again, you guys are going to want to start where you can, like the best place to start is where you can tell that your derivative will be 0. And that's going to be any hill or valley. Okay, the derivative of, so if your original function has hills and valleys, you can start by plotting zeros there. Okay? All right, so then, should we do, okay, so give yourself like some kind of, don't get too dramatic. Give yourself 1 hill and 1 valley. And it can be anywhere, any direction, 1 hill, 1 valley.
Okay, or just
1 hill and 1 valley. What I would do is at any hill or any valley, the derivative or the slope of the tangent line will be 0. Okay, so you got a little more complicated one, Trevor, but that's fine. So then you should put a point on your x-axis at any hill or valley, because the derivative that you're going to draw is going to be 0 there. Okay? So now, right? So then now, and again, we're drawing the derivative, just a sketch of the derivative. Now, the steeper the line, the further away from the x-axis you should be, because that's representing a really big slope. As it starts rounding out, you're getting closer and closer. So like if you look at Jillian's here, right here, that's not very much of a slope, right? That's like a fraction. So she needs to be very close to the x-axis, because those numbers are basically fractions. So now you're really concentrating on, are these tangent slopes positive or negative? And that's going to be represented as above or below the x-axis.
So